Okay. So, still now what we have done is we have used generating functions, okay, and we have basically calculated or predicted various properties of random graphs. Okay. So, this is done. What are the properties, basic properties which we have calculated? Can you tell me? Huh? Okay, average degree, then yeah, Z1, Z2. Okay. So, first neighbor degree, second neighbor degree, third neighbor degree. Okay. So, what are these important? First neighbor degree, second neighbor degree, how can those be important? Those can be again used to calculate. Huh? Yeah, you can Z1, Z2 is not directly giant component, but Z1, Z2 directly is used to calculate the diameter. Okay. And it also can, like in a typical peer to peer networks, how can you use Z1, Z2? That if you have a TTL 3 flooding, what is the coverage? If you have a TTL 2 flooding, what is the coverage? Okay. And then what we said is giant component. Okay. So, what is giant component? What exactly is giant component? Yeah, giant component is size of the order of the network. And what happens as you increase the degree, means it may not be degree only, you can increase some other properties, but what you have seen here, as you increase the degree, a giant component emerges. As you increase the degree, a giant component emerges. Okay. So, now with this, what is the topic today? Node removal. Can you tell me what is the relationship with this node removal with this? Very good. So, now the question is, given a network is characterized by what? Pk. Every network can be, as this is the most simplest way of denoting a network, Pk. What is Pk? Degree distribution. Okay. So, we know Pk is degree distribution. And then what can we have is a node removal technique. Node removal technique, which can be again characterized by Qk or Fk. So, what happens? What is Fk? Arpit, what is Fk? Probability that a node of degree k will be removed. Okay. So, it is actually probability that a node of degree k will be removed. Okay. Correspondingly, Qk is that after some attack, the probability that a node of degree k, what is Qk? Node of degree k has survived. Okay. Fk is probability it is removed, and Qk is that a node has survived. So, what is the question we are asking? Now, let us put it in a more mathematical concept, mathematical point. What is the question we want to ask? That given Pk and Qk, tell me, what will be a, can we derive a closed form equation to say that how long the giant component will survive. Okay. So it's extremely important, like many of the networks, means particularly see peer to peer network is highly dynamic. Okay. Internet by itself is dynamic. Okay. So many of these networks are dynamic, or most of the networks are dynamic. Okay. So in biological networks you can see that gene networks are dynamic. So you have to say that how long can this dynamicity be withstood. Okay. So this is the question which is asked, and most of the time we computer scientists do some simulation and tell that okay, this much up till this is time. But if you have a closed form equation, it takes your research to a different level. Okay. Clear? So question is clear. Okay. So we will use the same thing. Okay. Just before I go to the technique, I can ask you some questions, like if it is random removal. Okay. Random removal of any node means all nodes are equally likely. Okay. Removal of all nodes are equally likely. Then what will be Qk equal to? Will be equal to Q. Okay. So subscript K is not needed. Okay. It will be some constant value for all. Okay. It can be 1 by n or anything, but it will be a constant value for all networks. Okay. It is independent of K. Okay. And now if I think of an attack, let us think of an attack. So what does attack mean? What does attack mean? In terms of degree, can you tell me what does attack mean? Huh? What does attack mean? Removal of higher degree nodes. So higher degree nodes will be more likely be removed than lower degree nodes in an attack. Okay. So then what do I write? Like Fk, I will use the term Qk and Fk alternatively. Okay. So what will be Qk? Can you tell me in terms of attack? Just try. It will be K. Okay. It can be proportional to K. Okay. It can be proportional to K. So as K is higher, it is, and more generalization will be K to the power C1. It is a okay. So now just let us look into it a little more detail. Huh? Hmm. No, that is attack. So what I am thinking of the model, that what is attack model? Attack model is higher degree nodes will be removed more than lower degree nodes. See, there can be again a much more stricter definition of attack, like that the highest, the second high, if I remove 4 nodes, it will be the highest, the second highest, the third highest and fourth highest. So that can be a deterministic way of defining an attack. But in a network, in a large network, it is highly unlikely that you will get the highest degree node and then attack, but you can fairly get a higher degree node. Okay. So it will be more probabilistic. So I am trying to model that probabilistic concept. Okay. So, that is why I wrote that f k is proportional to k to the power c 1, agreed. So, now just means the simplest way would have been k, f k is equal to k, a proportional to k, that gives you idea. I am just making it a little more generic and telling k to the power c 1. So, now let us see the value of c 1. So, if c 1 is greater than 0, that means it is attack. So, c 1 has to be greater than 0, but what happens if c 1 is equal to 0? Huh? It becomes a random failure. Okay. And if c 1 is less than 0, what happens? The ones with the higher degree nodes will survive, the ones with lower degree nodes will vanish. And can you tell me some network where this happens? Means it happens in peer to peer networks, like if you join with dial up line, it is more likely that you will leave early. If you join with ISD, you will stay for long. If you join with DSL, you will stay for long. Okay. So, it is, if you see peer to peer domain, it is just inverse. Okay. So, see, it is called inverse attack. So, what is the interesting? By a single variable, you are basically able to capture the entire domain. Okay. You are basically able to capture the entire domain. Okay. So, problem definition is clear now. Okay. So, now I want to ask you some questions. The first question is that, can we write the generating function of, I want to write the generating function f0x. Okay. What will this show? That a node of degree k. Okay. What is g0x? Let us write first. It is pk xk. What does this generating function mean? The probability that a node is of degree k. Okay, generating function showing the distribution of the probability of a node of degree k. Okay. Now, my question is, I want to write a generating function of distribution of probability of distribution, generating function which each coefficient shows, the kth coefficient shows the probability of a node having degree k and have survived. Previously, it was probability of a node having degree k. Now, I want to write the generating function probability of node having degree k and have survived. Then what will be the generating function now? Pk into, very good, Pk into Qk to the power xk. So, it will be Pk into Qk to the power. Okay. So, then what will be f1x, means like g1x, I want to find out f1x. Okay. What will be f1x? It will be the same way. So, it will be same definition f0x by z. Okay. So, that is k pk qk x to the power k minus 1 by summation k pk. No, means I am just taking the z. So, the concept is like this, that I have removed some nodes, but think those nodes are off. Okay. So, the edges goes and everything goes. Okay. Now, the similarly I want to find H1x and H0x. You remember we found what is H1x and H0x in the previous case, please tell me. It was, okay, I will just revise. H1x was that you pick up a random edge, and you can reach a node with degree 1, you can reach, you remember, you can reach a node which does not have any out degree, you can reach a node with degree 1, you can reach a node with degree 2, okay, and these all are basically H1x. Once you reach there, it is a recursive definition, if you remember. So, we drew this picture. Okay. So, that is why H1x was what? Tell me the formula of H1x. 1 plus tell me what was the formula, check and tell me. X 1 because you have G1 of there is no 1. Is there a 1? There is no 1. 1 means you have gone one step and then this one. And what was H0x? G naught of again x, because you have picked up that node and gone. Okay. So, you remember this. But here in this case we have to do some corrections. In this case, what are the corrections? See, one case is happening that you are coming here, see this first case. Think of this first case. What can happen? This node, you come here, but this node is removed. Because of QK, this node is removed. That is a possibility, new possibility. So, beside this, there can be this. Okay. So, you can pick up a random edge, because you are thinking in on off term, you can pick up a random edge and come and see that there is no node. Okay. So, that has to be subtracted. So, how much is that? That you pick up one and you see there is no node. Okay. Let us write f1x. I think Moinak was bringing in a very good point. Okay. So, k, what was f1x? K pk qk x to the power k minus 1. Is it like that? By summation of k pk. What will happen if I take f10, f11? What should f11 give in a normal generating function? Any generating function, if I put 1, what should it give? It should give 1. Okay, sum of all the probabilities it should give. Means it is not a thumb rule, I mean it is not a rule, but it is a thumb rule or axiom which we tell that it should give 1. But is this giving 1? This is not giving 1. So, that means what is the correction term? Is 1 minus f11. Okay, means this is 1 minus f11 is telling what? The probability that if you pick up a random edge and go to the other node, you will see there is nothing. Okay. So, then you write h1x. So, previously see x is equal to 0 in this case, in this generating function x is equal to 0, there was no term in this generating function. If I put x, if I just wanted to find h1 0, okay, and but in g0 x, if I wrote g0 0, then what did we get, Dibbo? If we write g0 0, what did we get? p0, just p0 was staying, okay. So, but here nothing stays in this. If I put 0, nothing stays, because if I have, it is obvious that if I have pick up a random edge and go to some node, and try to find the component size, because there is no breakdown, the component size will necessarily be 1, at least 1. But in this case, since this node has been removed, the component size need not be 1. So, then I have this correction factor. What is the probability that the component size will not be 1? Means this p0, if I want to say, that is f11 1 minus f11 plus x. Now, I do not write g1, I write f1 h1 x. Am I clear? Okay. Once more, let us see this h1 x is equal to x g1 h1 x. Okay. What does this signify? That what will be the probability that the component size will be 0? Tell me from this. It will be 0, because the least term you can get is x term. Okay. So, what is the probability that the component size will be 0? Is 0, but that is true because you are not removing any node. But in this case, you have removed a node, you have removed nodes. So, there will be edges which are dangling, there will be edges which are dangling. Okay. So, you have a finite probability that you pick up a random edge and you reach and you see there is no component. Okay. So, that is why you have this correction. Similarly, for h0 x, you have this correction and you write 1 minus f0 1 plus x f0 h1 x. Okay. Am I clear, Nisha? Why is that? This one, huh? Here. Yeah, because G1 was, because I have changed from G to F, no. So, this was G0 x, but this is F0 x, means I am working with F0 now. So, just I am replacing G by F. Okay. Previously, I was working with G0 because no nodes were removed. I have now defined a generating function where nodes are removed. So, that is F0, and accordingly I am working upon it. Clear? Okay, great. So, with this again, with these two equations, what we can do, if we do h0 x, what does this give? If I differentiate h0 x, Madan, what does this give? What is h0 x? Tell me. If I pick up a random node, what is the component size, means what is the component size to which it belongs? And if I do h0 x, any generating function, if I take the differentiation, what does it give? Any generating function, if I take the first derivative, what does it give? Huh? Means h0 x at x is equal to 1. What does this give? H0 dash x at x is equal to 1. What does this give? What does G0 dash x at x is equal to 1 give? It is average. So, any generating function, when I take the first derivative is the first moment, second derivative is the second moment. Okay. So, first derivative is the average. So, this is giving S. So, average component size, and if I do some calculation or something, it will come in like this. It is plus f0 dash 1 f11 by 1 minus f1 dash 1. Okay. With using this and doing this calculation, you will see it comes simply that. Okay. So, now what more can we tell? What more can we tell? That again 1 minus f1 dash 1 will tell us the when the giant component will disappear. So, that answers our question, when the giant component will disappear. Okay. So, now if I go f1 dash, try to write f1 dash. What is f1 dash? Again tell me, summation of k pk qk and by summation of k pk. So, this becomes summation of k pk qk minus summation of k pk is equal to 0. No, I think I made a mistake. It is f1 dash. F1 dash is k into k minus 1. Okay. So, this is summation of k into k minus 1. So, I write it in a better way. So, it is summation of k into k minus 1 pk qk minus summation of k pk equals to 0. Okay. Agreed? So, you have summation of pk goes, k and k pk will be common, you can see k minus 1 qk minus 1 is equal to 0. Okay. You can write it in a better way if I want to write in terms of fk. Okay. So, k 1 minus fk minus qk minus 1 is equal to 0. So, summation of k pk k 1 minus fk, it will be plus fk minus 2 equal to 0. Okay. So, I can write in terms of qk or in terms of fk. Okay. So, this is a long standing work. I think it started in late 90s, or no, I think the first paper was around 2001 or 2000. I think it started around 2000. So, it was by Callaway and Cohen. Okay. Anyway, these are big names, Cohen, Callaway, and yeah, and finally this equation, this generalized equation has actually been discovered by Bibhash. Okay. So, this is the generalized equation you get, giving a qk and pk, you get it. Okay. Okay. Right. Clear. Very good. So, now let us go and put fk is equal to f. Now, let us take the general simple situation where first situation is fk is equal to f. the random failures. So, put it here k p k k 1 minus f plus f minus 2 is equal to 0. Okay. Or I can take the first one also, that means k f k means also q. So, take this equation, summation of k p k k minus 1 into q minus 1 is equal to 0. Okay. So, I q, since q does not depend upon k now. So, k minus 1 into k p k is equal to summation of k p k. Okay, I just took the q out and puts k p k this side. Okay, agreed? So, this is what k p k, summation of k p k is average degree, or I write average degree this way. Okay. So, now see q, what is this? K square p k minus k p k. What is this? This is the second moment, this is the second moment, and this is the first moment. Okay. So, what is q coming to be? Q is coming to be 1 minus k square by k minus 1. So, see this part. So, this is the QC, okay, QC, the critical Q. This is the critical Q which is needed to be removed. Yeah, means critical Q or the opposite will be FC, that will be the critical least F which is needed to remove the giant component. Okay. So, similarly actually you can do it. So, do this for q k is equal to 1 minus alpha k to the power c 1. Okay, I just we had put f k is proportional to k to the power c 1. So, I put f k is equal to alpha k to the power c 1, and I basically I am doing for the inverted attack. Okay. Okay, I am just doing it for the inverted attack. Yeah, I am considering C1 is always positive. So, C1 is positive, that is why I wrote it like that. It's just I change a convention, or if we want to follow the previous convention, then we should write some. Yeah, I think this is fine, we can follow this. Then what happens? So, you can go on again take this equation and k p k k minus 1, okay, 1 minus alpha k c 1 minus 1. Okay. And you can see that it will be k square minus alpha k 2 minus c 1 plus alpha k 1 minus C 1 minus 2 k. Okay. So, actually as long as C 1 is less than 1, this equation behaves in a good way, but if C 1 becomes greater than 1, it does not behave very good. Okay. If C 1 becomes greater than 1, there will be a negative exponent here, and this equation will not behave very well. Okay. So, is this clear? Okay. So, now seeing all this, then actually this is purely what we did, that we wanted to ask another very simple question, that instead of doing all this, can we take a network, Okay. So, what is happening, basically some nodes are getting removed. Okay. So, before removal the node has pk, the network has pk, and after removal the network will have, can be pk dash, or I write pk dash, okay, p dash k, or what you say, pk dash. So, just given a network and after the node removal technique, if I can find out p dash k, then I am done. Then I can use the, what is the original equation? Given a network without any removal etc. Given a network, when do I know the giant component emerges? What is the equation? Something like this? Is it something like this? Or it is k into k minus 2 pk. Okay, this was, so now I have pk. Now I have some removal, okay, some removal process going on, okay, and then I will have pk dash, okay, and I can, without this elaborate mathematics, actually if I can find out this and see whether this is greater than 0, if as long as it is greater than equal to 0, I will say that the network has not broken down, and if it becomes less than 0, I say that network is broken down. Concept is clear, idea is clear. Okay. So, what is the question I am asking? That what is the problem statement now? Given pk and given a qk, can I find the pk dash? So, previously was I am given pk, I am given qk or fk, whichever you want, I want to find pk dash or p dash k, whatever else. So, given this two, can you tell me this? Okay. Question is clear? Yeah, this is the original equation. Pk is the, or means originally what we said, pk is the degree distribution at which the giant component appears. So, if I forget about any dynamics, if I am given a standard pk, I know how to calculate at whether there is a giant component or not. So, that way I am having a pk, I go for qk, and then I just calculate p dash k, and this can be fed into this equation again. So, this equation, the previous thing what happened, this equation has been modified and we have got this generalized equation. Okay. This equation has been modified and we have got this generalized equation. Okay. So, if you can put, see here, put qk is equal to 1, put qk is equal to 1, what is happening? see there is no removal, it is becoming the original equation. If Qk is equal to 1, it becomes actually k into k minus 2 pk. Okay, it becomes the original equation. It should. Okay. Qk is equal to 1 means what? No removal. Okay. So it becomes the original equation. Clear? Okay, very good. So now, so my question is, I do not want to change the equation, I want to just predict the degree distribution. Given a pk and given a qk, find the p dash k. No, that won't be equal to pk into qk. Very good question. So why won't that be into pk into qk? It is because, see, I have a node. Okay, I have not been removed. Okay, but many of my neighbors have been removed. So pk into qk actually does not capture that. Okay. It sees whether it has been removed or not removed, but it does not capture that even if this guy is standing firm, many of its edges have gone and its degree has actually decreased. Okay. That does not come into simple pk/qk. Yeah. So somehow you have to check the distribution. So let us go to this part now. Okay. So again I ask the question that removal of a node along with its adjacent links. So this is the point which Nagarjun was putting forward, that removal of its node along with its adjacent links changes the degree of its neighbors. Okay. Hence changes the topology. Now given the initial degree pk dash, probability of removal is fk, we represent the new degree distribution p dash k as a function of pk and qk. Okay. I think problem statement is clear. So see this first. Okay. So this is a network, where the left sides are nodes which have survived, while the right sides are nodes which have been removed. And now my objective is, what is my objective? Is finding E, the number of edges which are there. Okay. So here I know what are the number of nodes here, tell me. It will be summation of n pk qk. This is summation of n pk qk and this is n fk, n pk fk. So number of nodes I know, okay, but their degree distribution I do not know, and I want to find the number of edges which are passing. Okay, am I with you? Okay, great. So now see, I think in terms of tips. Tips means a edge has two tips. A edge has two tips. Okay, two ends of a edge. So edge has two tips. Okay. So now total number of tips in the surviving node, tell me. It was, see, again total number of nodes is pk qk. pk qk means pk into 1 minus fk, or I am using j term, but this would help. It is just to not confuse with the scripts. So pj 1 minus fj, n into pj 1 minus fj is number of nodes, and each node will have j degree. So j into n into fj pj will be the number of tips. See, let us think, what is npk? Now, what is kp? N into summation of kpk. What is this? Tell me. What is n into summation of kpk? 2e. This is not e. Okay. Just remember this is not E, so it is 2E. So, when I write J n, okay, forget the J, forget the n summation of J P j 1 minus f j, it is actually showing the total number of tips, means 2E. Okay. That is why total number of tips, I am not telling total number of edges. Okay. It is showing total number of tips present in this part. Okay. Am I okay? So, now a tip may have the other end this part or the other end this part. Okay. A tip may have the other end in this part or the other end in this part. Okay. So, now I go to this part. Okay, Ashish, I go to this part. Okay. And then I say that I pick up a edge, I pick up a tip. Okay. I pick up a tip. Now, how many tips are left? See, in the whole network, how many tips are there? K n k. And if I pick up a tip, how many tips are left? K n k minus 1. So, now my question is, given a tip, what is the probability that if I pick up a random tip, it is the other end of that tip? Given a tip, I have already picked up a tip. So, a tip is with me. Then I pick up another random tip. 1 by k n k minus 1. Very good, Arpit. Okay. 1 by k n k minus 1. So, and how many tips are there? How many removed tips are there? How many removed tips are there? All tips here are removed, and the number of removed tips here are, I have written n j. So, we can write, just for your sake, n j is actually n p j. Okay. N p j. Okay. So, these are the number of tips which have been removed. These are the number of tips which have been removed. Okay. Okay. So, am I with you? Okay. So, what is happening is, basically these are the number of tips which are removed. So, the total number of edges. So, I again come to this, that the probability any tip I pick, that it has the other end, this side is the probability, if I pick any tip, it has the other end, this side is this much. I am picking up any tip and it has the other end, this side is this much. Am I clear? Okay. So, now how many tips are there at this site? Is this much? Number of tips in the surviving side is j n j 1 minus f j. So, if I multiply this into this, then what do I get? I am basically multiplying this into this. Okay. Then what do I get? The number of edges. Immediately I get the number of edges. So, what is happening is summation of j n j f j by summation of k n k minus 1. Okay. K n k minus 1, and what is happening, that this is given, this is, what is this? First let us freeze this. What is this? Now, if I pick up a tip, if I pick up a random tip, yeah, then the second tip will be in the removed set. If I pick up a random tip, then the second tip will be at the removed set. Akshay, thank you. If I pick up a random tip, then the second tip will be at this position. Okay. Am I clear? So, if this is given, now how many tips so this first, if I pick up a random tip, so from where can I pick up the random tip? I can pick up the random tip from the surviving set or the removed set. It can be based, it can be both, it can be from the surviving set, it can be from the removed set. Huh? Now, I just see the surviving set, and that is why I multiply this with summation of j n j 1 minus f j. Okay. And this actually gives you number of edges. This actually gives you the number of edges. Okay. Clear? So, once I get the number of edges, then I say that I want to find out phi. What is phi? That probability of finding an edge in the surviving left subset, means surviving set, that is connected to the node of the removed set. Okay. So, I have an edge in the left set, I have an edge in the left set, okay, and its other set, other is in the removed set. Means I just want to convert it into the probability. So, probability will be total number of edges present. Okay, total number of tips present. So, these are the number of tips which has another tip this way, and just if I divide it by total number of tips, I get basically number of probability that each tip has a edge that way. Okay. So, the phi is clear. So, once it is phi, removal of a node reduces the degree of the survived node. Okay. Removal of a node reduces the degree of the survived nodes, first of all. And now, node having degree greater than k. So, removal of a node reduces the degree of the survival node, because what is happening is I have a node and I have removed this node, and this node is not removed, but in essence this degree is getting less. Okay. In essence this degree is getting less, this is clear. Now, what is happening? So, what is happening that I am having degree greater than k, and if I have been removed, if I think degree greater than k, say I have degree k plus 1, and if one of my neighbors have been removed, then I will become degree k. If two of my neighbors are removed, then also I can become degree k. If three of my neighbors have been removed, then also I can become degree k. Okay. So, now first let me think probability that a survived node will lose one edge. I just want to think what will be the probability that the survived node will lose one edge. Okay. So, what can that be? The probability that a survived node will lose one edge. Again, it is the same thing. It is the same phi. Okay. So, once you get the phi, once you get the phi, now the question is that probability you can find that it will lose 1h, 2h, 3h, okay, continuously, okay, it will and will 1h, 0h, 1h, etc., okay, to become k. So, what you can do is you now want to calculate p dash k. What is p dash k? That it was q originally, it was q originally, and q can be anything from k to infinity, and it has become k by removing q minus k nodes. Okay. And what is the probability of removing q minus k nodes? Phi q minus k. And what is the probability that not more than those are removed? Is 1 minus phi k. So, once you have this p dash k, you can basically get the new degree. Okay. Basically you can get the new degree. Okay. And once you have the p dash k, basically you can do everything. Okay. I know it is a little bit involved, but yeah. So, again I will put this up in the net, but you can see there is a physical review e-paper of Bibhash again. Okay. This is I think it is published in 2008. So, I will put this up, but this captures this concept. Huh? Yes, slides I will surely put up, but also this I will put up. Okay. Thank you very much.